lesson in the electromagnetic wave spectrum. We're going to look at other wave phenomena that happens with light and other electromagnetic waves. Specifically, when we talk about white light, we're talking about incoherent white light. If you're looking in the room around you, you're going to see white light because all the colors are mixed in. They're not kind of in cahoots. They're out of phase. They're just all over the place. So incoherent is kind of like not just all over the place. But the mixture gives you the white light that you see. When you have this thing called monochromatic light, you're seeing a single color of light. So red light could be considered monochromatic light. And monochromatic light can even go to the next phase. Let's take a look at this right here, this slide. It could be incoherent. Incoherent, so it's red because of the wavelengths being the same. It's red because the wavelengths being the same. But if you use a special device like a laser, you're amplifying that red light because you have those waves all in phase. That's going to be different. So that the being in phase, and the laser will do that. Laser will do that using a crystal and a power source to create that wavelength that's coming in all lined up like that, all amplified, and therefore a laser will produce a much more powerful light. Light also has an alignment. When you think of electromagnetic waves, they have we have a electric field and a magnetic field at a 90-degree angle from each other. So light is an electromagnetic wave, so it has that, and those alignments can be all over the place. So they don't have to be all lined up. If I was going to draw them all lined up, they might be all this way. And we can use sunglasses and polarization, and this is so polarization is going to be the alignment. That's when we hear about polarization, that has to do with the alignment. If they're horizontally or at some sort of random angle like you see here. And polarized film, what polarized film can do, and polarized film, any type you have will have a transmission plane. And so if it's a horizontal transmission plane, it will let 100% of the horizontal light through, but it will cut out light more and more and more until you get to the vertical plane. If any light was coming in vertically, it would cut 100% of that light through. And so polarized film, you can still see through for the most part. It's just going to cut out completely just some of the light. If you have two sheets of polarized film and they happen to be, if you take a look right here, if one is horizontally aligned, it's going to not let any of the vertical light through, and another one is vertically aligned, like the one you see right here, it's not going to let any of the horizontal light through, and in cahoots, they're going to cut out all the light if they're aligned at a perpendicular to each other or a 90-degree angle from each other. Now, the film itself has a little bit of tint, so if you have them both horizontally aligned, it will look a little darker, but you're not going to cut out the light coming through. So perpendicular alignment, if you have a horizontal transmission plane and a vertical one, you're going to block out 100% of the light. Now, with sunglasses and how they work, when light's coming from all around you, specifically the sun, you have all randomly polarized light rays coming at you. When they bounce off a surface, like a car in front of you or the ground, you'll have them that light will start getting aligned. They'll be horizontally aligned. And if you have horizontally aligned light coming at you, and you have vertically polarized glasses, well, you're going to end up cutting out that glare coming through. You'll still let all the different random angles come through, but you're going to cut out 100% of the horizontally aligned light that's coming off the ground or off of a car in front of you, and therefore your sunglasses will help you cut out that glare, and you won't see that extra glare. So why are they important to stop glare? Sunglasses, because of the alignment. The vertical alignment cuts out the horizontal glare coming at your sunglasses. Which of the sunglasses in figure 1 would cut out the horizontally polarized glare? Go ahead and answer that question. That's going to be right here. The B will cut it out because they're vertically aligned, so they're going to cut out the horizontal glare. Would a person wearing sunglasses labeled D see? What would a person wearing these sunglasses see? And they would see one light, they would see the glare, and the other light would have all the glare cut out. Another property called Huygen's principle. it talks about waves and waves in general. It says that if you have a wave coming around, every single part of the wave acts like a wave in itself. And because every single part acts like a wave in itself, this side right here is blocking that wave. But once it's allowed to come through, this particle, which acts like a wave in itself, just keeps on expanding out. And the result is that you have a bending that occurs around a corner, and that's diffraction. So the new wave point and created wave is not stopped by the corners once the wall is passed, and that's why that will become bend around it. And when we talk about diffraction, wavelength is going to matter, especially when you're talking about the different waves of the electromagnetic spectrum or light in general. Longer wavelengths diffract more than shorter wavelengths. So let's take a look at the colors of light specifically. Red has a longer wavelength than a violet, and therefore, the longer the wavelengths, the more diffraction you're going to see in red versus a violet over here that has a shorter wavelength or a higher frequency. Diffraction grating will use that whole idea that your colors of light coming through and they're bending differently, and when they bend differently, they're trying to go through. There's a bunch of slits in a film when you hear about the term diffraction gradients. All these are just lots of slits in this film, and then the diffraction pattern, the diffraction that occurs from all the different wavelengths in that white light will cause it to bend out, and you'll end up seeing, if you ever see a diffraction grating, you're just going to see a bunch of, I should have had a little animation of it, but you're just going to have a kind of a kaleidoscope of colors that show up in this grating, instead of seeing, if you don't shine light through it, you can see something that looks kind of light, but once light gets shine through that, or if you just put diffraction grating close to your eye and look at the light, you're going to see all the colors of light kind of separate through. Another thing you'll hear in physics that helps define some of the properties of light and how light is a wave is doing experiment where you have a thin slit and you shine light through it. And when you shine light through it, first of all, when you see all these different lines coming in, those are considered wave fronts. Wavefront is an area of a wave that is in the same phase. And then there's these blue lines after the whole going through the slit. These blue lines are they're just drawn there purposely to show you the different wave fronts that are occurring. When you shine light through a single slit, you should, if light was a particle, just see a little dot right over here. When you shine let's say a red monochromatic laser through that little dot, but instead you see a pattern that occurs. And so in this pattern, you're going to see a couple things going on. You're going to see this thing called a maximum, which is going to be like the central area. The maximum is going to have, it's going to be larger and smaller depending on how much diffraction is occurring. And therefore, like a red light is the Roy G. Biv, you got R. The red is going to have the largest wavelength and therefore have the largest diffraction and therefore also the largest maximum that will occur. And these little patterns that you'll see light, not light, light, not light, light. And so where you see light right there, you're going to have constructive interference occurring. And where you see the dark right there, and there, you're going to see that it's going to be a pattern of destructive interference, which takes away the light because of the interference of the light. And so that gives you the pattern that you'll see that will be captured by a film that you're going to, you'd look at. Would orange or green light diffract most and why? So orange or green, think about the wavelength, which one has a bigger wavelength, and orange is going to, because orange is going to diffract more because it has a bigger wavelength. With radio waves or orange light, so taking a look over here, radio waves or orange light, which one would diffract the most? And that's going to be radio waves, because radio waves have a larger wavelength and therefore would diffract more. Then here's this question. What's the reason for the maximum, once again, the central light area for red after a single slit diffraction to be so much bigger than, let's say, green light? And that's going to be because red diffracts more. So since you have more diffraction, you're going to have a larger area. It's going to have that maximum, or that central region will be much larger for red light versus a green light. The brighter areas projected here are from, and so labeled A, are from what kind of interference? And that's going to be constructive interference. And then the darker areas are going to be from what kind of interference? That's going to be destructive interference. And lastly, sometimes you'll see a thing called double slit interference, and you'll see even more of a pattern where you shine a red light through, and so you have a red light coming through and going through these two slits. The further the slits apart, the greater the interference patterns that will occur. So there'll be more nodes, constructive interference, and antinode sections. So instead of a really large maximum and a few the next area of light, you're going to have a much more interactive pattern, many more slits and many more lines going on. So more nodes and more antinodes. Remember, nodes are constructive interference and antinodes are destructive interference. It's going to be where you see the most light would be the antinode, and the nodes is where you would see the light. And an optical screen would be somewhat out here to capture that, and you'd see the pattern. So there's a single slit, but you'd see a pattern that would occur from a double slit too. Lastly, just light is considered a wave because you can see all the different, remember the four phenomena. Diffraction and interference can be seen when you look at the single slit or double slit experiment. You have light coming through, bending around the corner. In the process, it's going to interfere with the other light, and then you're going to have light, dark as a result of constructive and destructive interference, constructive being the lighter areas. Reflection can occur. When you look at yourself in the light, in the mirror, you're going to see your reflection. So there's an example of reflection occurring when you're using light. And then lastly, if you use a prism, you're going to have refraction going on, a bending that will occur. And we talked about prisms in another lesson, but prisms will separate the light. So light has all four of these different properties that all waves have. So therefore, a light does act like a wave.